Hey there everyone, we are going to do 7-3 today. We're talking about geometric models for probability. So this is the sample problem from our text, but I'm going to do it slightly differently. I think that my method is much better. Anyway, just as a bit of review though, if you understand the problem, we're talking about two friends that are going to go online from 8 to 8:30. When they go online, each one will wait 10 minutes. So if you think about their login time, the difference between those two numbers has to be 10 minutes or less, and they will be able to meet if that happens. So to review, think about this as like a 7-1 problem where you're doing simulation. I've got my calculator here. I have it set for random numbers between 1 and 30, and we could tack an 8 onto that to make it the time they log in. So I just have hit two numbers, one for each friend, and I've got 7 and 22. Then I can hit two more, and I've got 20 and 4. And I get two more, and I've got 17 and 23. Now my question is, if friend 1 logs on at 8:07 and the other one at 8:22, the difference there is 15 minutes, and they will not meet. So that's a bad outcome for those friends. These guys are within 16 minutes, so that's also a bad outcome. These guys, though, are within 6 minutes, and so that's a good outcome. We could do a whole bunch of trials, and we could work out the ratio of happy outcomes to sad outcomes, and we could do a simulation and answer it. But we are trying to build a way of doing this in a theoretical form. And the way to do this is to think about it as we started to in 7-2, and that's using geometry. So the way the book introduces it is good, and that is by thinking of an x and a y axes. Friend 1 will be down here, friend 2 will be up there, and each will wait for between 0 and 30 minutes. Again, I think if you take off the 8, it just makes it simpler, but obviously that's 8 to 8:30. Same thing here, 0 to 30. And so friend 1 can log in anywhere along there. It's a continuum, so these will be continuous outcomes. Here we're modeling it using discrete numbers, but you'll see that you can wind up with the same probability doing either method. Okay, so the chance that they do meet is when the numbers are very nearly the same. So our sample space is going to be out to 30 and over to 30 like that. And we know that if they both happen to log in around the same time, along this line here, this is going to be where their outcomes are good and they will meet. Okay, so it's nice to sort of have a mental picture of what that's going to look like. Think about it in terms of if one friend logs in at exactly 8 o'clock, the other friend has until 10 minutes to log in right there. That's the 10-minute mark, that's the 20-minute mark. Okay, well, just to repeat, if friend 2 logs in at 0, friend 1 has to log in by 8:10 or they've missed each other. If friend 2 logs in at 30 minutes, then friend 1 must have logged in over here by the 20-minute mark. Again, if you think about it just in terms of the numbers being within 10 units, I think it's fairly easy to come up with these two coordinate points. And then you just connect them like this. It's going to be parallel to this happy zone going down the middle. The converse is true then. If friend 1 logs in right at 8 o'clock, friend 2 must log in by 8:10. And if friend 1 logs in at 30-minute mark, if friend 1 logs in at the 30-minute mark, then friend 1 has to be in at the 20-minute mark. So I think I mixed my words around, but you see, you get that same type of a slice coming through parallel to this. So these numbers are out here. This might be, for instance, 5,25 for a point like right about there, and that's not going to be good because their separation is 20 minutes. So that can help convince you that these are the bad zones, the unhappy outcomes, where they do not meet, but this zone in the middle is where they do meet. This then is a 20-minute boundary, and that's a 20-minute length right there. This is also 20 minutes, and that's 20 minutes. So the question is, what's the ratio of this good zone to the entire zone? We want the probability that they do meet, all right? Well, I think it's most easily done if we figure out what's the probability they miss, because this triangle and this triangle are fairly easily found in terms of their area. If I just move this one up. I've got a square that's 20 by 20. So 20 squared over 30 squared is the probability that they do not meet, which is 400 out of 900, or 4/9. So the probability that they do meet will be 5/9. Okay, so I'll just sneak it in up there. That's the opposite of them not meeting, is that they do meet 5/9. All right. So the book uses equations that are based in inequalities. That's all mathematically good, but I think simply going with the geometry and working out the concept of these two numbers being within a unit, within 10 units of each other, and then dealing with extremes along the axes is the easiest way to go. All right? All right, we're back with the second problem, which represents the other type of problem you often get with this sort of geometric model for probability. And this is one where two things together add up to something that's more than an amount, rather than whether or not two numbers are within a certain range. So this problem, we're going to pretend that the swim team is having an end-of-season party. Mr. Young is responsible for buying the food, and he's got he has to stick to within a range of $50 and $150. It could be anything along that range with equally likely probability, while Emma is responsible for buying the decorations, and she might decide that nothing is suitable and go down as low as 0, but could spend up to $100 if she finds something that's pretty snazzy. So, but there's only $200 in their budget, and they're going to compare notes after a day's shopping, and we want to find out the probability that they have overspent their $200 budget and have to dip into other funds. All right? So the first thing we need is a really good graph. Okay, like that. Now what we're going to do is we're going to look at, this is Mr. Young's spending parameters. This is Emma's right here. She can spend up to $100. That's supposed to be 100. And so the 50 range begins there. The 200, whoops, that's 150 is to right there. And then this budget is from 0 to 100. So this is the region that they will be shopping within. That is our entire sample space for this problem, for both of these. Now, what part of that, what fraction of that represents overspending? Well, again, I think it's much easier in these problems to think from the extreme. So, for instance, if Mr. Young spends all of his $150, then Emma can spend up to $50 right there. And you can write that down, 150, comma 50. That's where the break-even point is for their budget. If Emma spends all 100, then Mr. Young can spend up to $100 right there, and that's where they break even with their budget right there. Anything above that is going to be in this direction. This is where they've overspent. Okay? So that would be where it's 150 and 100. There's an extreme. Try points in here just to convince yourself that that's a problem, that it works that way, with this line connecting them. If you think that's going over to 100, whoops, and there's up to 100, but going over to 125, for instance, would go up to 75 right there. So now what's this area? Well, if that's 50 like that, and this is 50 right here, then this is half of 50 squared. All right, that's this area bounded by that triangle that's 50 by 50 cut in half. Then this entire area here, well, that's from 50 up to 150, so that's 100 that way. And this is from 0, so this is 100. So this is 100 squared then is the bottom. And so I'm going to get, well, 50 times 50 is 2,500. This is going to be 1 with 4 zeros. That's 10,000. I can cancel zeros. Now this is, I have to cut this in half, right? So I can just double the denominator. And so I've got 25 out of 200, which is going to be 1/8. All right, so the probability there is 1/8. Another way to think about it is just to draw it like this. And you can see each one of these is a quarter, and that's half of a quarter, so that's 1/8. So that would be the probability that they overspend, would be 1/8. All right? Good luck on the homework.